A very good afternoon to everyone. This is V.S. Rajashekar, a project associate at Guidance Control and Decision Systems Lab of Aerospace Engineering Department at Indian Institute of Science, Bangalore. Today I will be presenting an aerial gripper mechanism which is based out of a 6-bar mechanism and discuss its kinematics and dynamics of it. The overview of the presentation is as follows. In figure A, you see the sketch of the mechanism. It is basically two 4-bar mechanisms put together in a loop. So figure B shows the opening of the gripper and figure C shows the closing of the gripper. Figure D is the CAD model of the gripper and figure E is the prototype that was made, and in figure F the hexacopter carrying a spherical object is tested. Our work in brief. This work is based out of a 4-bar mechanism, and another two links are attached to that at points 2, 5 and 4 in figure B, and they form a 6-bar mechanism with 7 revolute joints in it. The working of the gripper mechanism. The working of the gripper mechanism is as follows. The link 1, 2 actually actuates to and fro. In figure A, when the link 1, 2 is at the back, it is in the open position, and when in figure B, when it is at the front, it is in the closed state. So this is how it opens and closes, and is used to carry and is used to capture objects of interest. The dimensions of the link are as follows. The notation used to represent the dimension of the links of the gripper mechanism is given. A, B, C, D forms a loop, and A, E, F and D forms another loop. The dimensions of the linkages were presented in the earlier work and can be referred to the reference at the bottom. The dimension synthesis was done in that work called Synthesis of a 6-bar gripper mechanism for aerial grasping. And the link lengths, the 6 links are there, and the link lengths, link width and link thickness are generated. This was done using a geometric programming method, which is dealt very well in the reference given below. In this work, we are going to talk about the kinematic analysis of the mechanism. As you can see here, theta 2 is the angle which is actually actuating the mechanism, and the theta 4 and theta 6 are the angles which are the output angles. This mechanism is based on two loops. So there are 2 loops in the mechanism, one 4-bar and the other can also be treated as a 4-bar, which are written using the vector loop equations. And in loop 1, theta 4 and theta 3 are found out, and in loop 2, theta 6 and theta 5 are found out. The moment of theta 4 and theta 3 with respect to theta 6 and theta 5 have to be equal. Only then we can obtain a good mechanism. So the mechanism is actually presented in the previous work, which was shown earlier. The plot of the input and output angles are shown in this figure. In figure A, we can see the theta 2 with reference to theta 3 and theta 5. They are almost parallel to each other. And in figure B, if you see that the output angles theta 6 and theta 4 with respect to theta 2, which is the input angle, is in a position to grasp the object. The position of the joints and couplers are shown in this slide, where x0 and y0 are at 1. The point 1 refers to x0 and y0, which is treated as 0, 0, and the rest all points are treated as follows. And we form the position of the joints and couplers. Balancing of the mechanism. One critical thing when it comes to an aerial gripper mechanism is that the mechanism has to be balanced in such a way that even in a grasped state or in non-grasped state, it has to actually go through a number of vibrations. So this vibration will cause an imbalance in the mass, and it will actually help help the system become unstable. So this is tackled using the method of principal vectors. So this is the equation which is written on the bottom. Considering the masses m1, m2, m3, m4 and m5. So the balancing of the masses are done using the RS vector, and the RS vector is actually condensed and written at the bottom. And finally the principal vector, that is RS, is equal to h1 vector plus h2 vector, h3 vector plus h4 vector plus h5 vector are shown. Balancing of the mechanism. The numerical analysis is used to test the balancing of the mechanism. So in this graph, whatever you are seeing now, this graph shows that there is an imbalance in the position of the gripper. So the angle of operation of the gripper would be somewhere between 150 to 180 degree, but there is an imbalance in this region. So what we do is we add a counterweights for statico-dynamic balancing. In the first weight is added to the crank, which is shown in green, and the second is we extend a link outside so that it is already statically balanced. So this is the green signals, the green markings are those which represent the counterweights. Then coming to the dynamic analysis, the Newton method was used, Newton-Euler method was used, and the links, various links are drawn out, and the forces acting in these links are shown here. So we'll form the equations of motion. We write down the force balance equation, and then a numerical study of the current mechanism is done. So you can see the matrix, which is 15 cross 15 matrix, which was formed from the previous set of equations. And now we take B is equal to A inverse C by 1000. 1000 is for measurements. So like we are initially treating it as in some measurement unit, and later converting it into Newton and torque, Newton and Newton meter. So as you can see here, the torque, which is at the bottom, T12, is equal to 0.125 Newton meter. The fabrication and testing of the mechanism is done, where the initial CAD prototype was made using a CAD software, and in figure B you are seeing the 3D printed parts of the same gripper mechanism. Experiments were conducted in the outdoor environments, where you can see in figure 1 it is the static position on the ground, and figure 2 it goes up and tests openness and close, and in figure 3 you see the ball being grasped by the aerial mechanism. And coming to the conclusion works, in this work we designed a 6-bar aerial mechanism, and kinematic analysis, statico-dynamic balancing, Newtonian solution method was used for dynamic analysis, which yield the forces acting on the links and torques required for the driving mechanism. And the claw of the gripper was designed in order to grasp a spherical object. The analysis presented in the work will be used for controller design. The authors would love to acknowledge the Robert Bose Center for Cyber Physical Systems at IIC Bangalore and Khalifa University for their partial funding for this work. Thank you.